hear a lot about stem cells these days. Whether or not you're a biology major, I'm sure you've heard of Dr. Shinya Yamanaka, who won the Nobel Prize in 2012 for his work on stem cells. But what are stem cells, and where do they come from? What do you know about them? Why are they referred to as the most dramatic scientific breakthrough of our time? Tonight, I'd like to introduce you to the concept of stem cells and show you some examples of their therapeutic applications and potentials. To begin, let me first describe briefly what the stem cell is. As we all know, life begins with a single cell, the fertilized egg. When a sperm fertilizes an egg, it's a fertilized egg. So this cell then divides to produce two daughter cells. These two daughters divide to produce four daughter cells, and their daughters divide again, and so on. At certain stages, however, most cells stop making copies of themselves. We call that self-renewal, and start to specialize. And we call that differentiation. When we are fully formed, most of our cells are differentiated. These different cell types work in specialized groups. Some transport oxygen through the circulation system. Some carry messages between our brain and the rest of our body. Some form a physical barrier that protects our body against infectious agents. You can think of stem cells as a reservoir because the specialized cells can no longer make copies of themselves. If they die, they have to be replaced from somewhere. This is where stem cells come into play. We always have to make new stem cells so that they're not completely exhausted, because otherwise we would lose the capacity to make new cells at all. So the stem cell has to make a decision every time it divides and produces two daughter cells. Those daughter cells can be new stem cells, shown here, or specialized cells. Stem cells in the adult tissues can only make the cells of that tissue. So a stem cell in the skin can make cells of the skin, but it can't make blood cells, and vice versa. Stem cells are already quite useful in medicine. Theoretically, one skin stem cell alone can give rise to enough specialized skin cells to cover the entire body. When a person is severely burned, when we have a severely burned patient, we take skin sample from an unburned area and extract the stem cells out of it. We then seed these cells in a culture flask and grow them in the lab. They will keep dividing and dividing until they cover the entire bottom of the flask. Then this sheet of skin cells is transplanted to the burned patient. This skin transplant is crucial because the skin, as the outermost layer of the body, offers the first line of defense against the foreign pathogens. Without it, we cannot survive. However, we cannot reconstruct, for example, hair follicles or sweat glands that are supposed to be in the skin. Many labs around the world are trying to address this issue, but that's the limitation of modern stem cell technology. Let me now go over what's called the embryonic stem cells. Back along the chain of development, there's another kind of stem cell. In the early embryo, there's a group of cells that can give rise to all the tissues of the body. It's called the embryonic stem cell. What that means is we can take the cells from the early embryo and grow them in culture. And these embryonic stem cells can become heart, blood, brain, or skin cells, depending on the way they're grown or the environment in which they're grown. A stem cell goes through a long series of decisions to become a specialized cell. The combination of internal and external signals guides each stem cell along the path towards specialization. So by figuring out how to recreate these signals in the lab, scientists aim to grow pure populations of almost any cell type. The challenge then is to understand every step of the decision and how it is controlled, and how to actually provide those signals to guide the stem cell to differentiate into the desired form. There are efforts being made to make stem cells for the brain from the embryonic stem cells. But what happens then is these so-called neural stem cells in the brain, are no longer able to make every type of cell. Those neural stem cells can only make the cells that are in the brain. These lab-grown stem cells can provide useful models for drug screening and therefore may reduce the need for animal testing. The embryonic stem cells also have a therapeutic potential to treat diabetic patients. As you know, diabetes is a disease characterized by high blood sugar caused by insulin deficiency. Insulin is produced by cells in the pancreas, which are called beta cells. Transplantations of those cells can be done with modern technology, but the major obstacle to this transplantation is that we have a very few donor cells available. So what the investigators are trying to do is to identify the path between the embryonic stem cell and the insulin-producing beta cell, and eventually be able to produce as many beta cells as we want in the lab. This would allow them to stop relying on organ donors and perform transplantation on many diabetic patients at a much lower cost. Stem cell research is only a fledgling field, and most of the research on stem cells were done within the past decade. So you shouldn't expect a miracle all at once, but progress is being made, and hopefully in the next several decades, what now seems like a daydream may come to reality. There are not just the technical issues, but we see many heated debates around various legal, religious, ethical, and political issues with regards to stem cell research, and those are another obstacle we have along the way. I hope my speech today gave you some insight into stem cells and sparked your interest about stem cell research. Thank you.